Pluto is a far-off dwarf planet with a mysterious past that was previously a member of the planetary family in our solar system. But surprising new revelations from MIT's Michio Kaku and prominent astrophysicist Neil deGrasse Tyson have thrust Pluto back into the public eye. They indicate that this ice world may be headed for a collision with Neptune. However, how might this occur, and what would be the fallout from an incident of this magnitude? Is this approaching cosmic collision the result of something greater, or are we simply seeing an unusual astronomical phenomenon? Come investigate the potential impact between Pluto and Neptune. Astronomers continue to be fascinated with and investigate Pluto, a former planet that was reduced to a dwarf planet in part because of its unusual orbit. Leading scientists have recently predicted that Pluto's course is quite near to Neptune's, which has astrophysicists Tyson and Kaku concerned about the possibility of a disastrous collision between these two planets that may be extremely harmful and perilous for Earth. But how might such an occurrence even occur? Unlike every other planet in our solar system, Pluto takes an incredible 248 years to complete an orbit around the Sun. This means that, since its discovery in 1930, the planet hasn't even completed a full revolution. The mystery doesn't end there. Pluto's orbit deviates dramatically from the near-circular orbits of the main planets, as seen by its very elliptical form. Pluto's orbit is even more unusual due to its 17 degrees inclination toward the ecliptic plane. In comparison to the other planets, Pluto travels a somewhat steeper route. Its circular shape and inclination give its orbital pattern additional layers of complexity. The point where Pluto's orbit intersects Neptune's course is among its most fascinating features. Remarkably, Pluto actually approaches the Sun closer than Neptune does throughout each orbit, which goes against what one might anticipate given their relative positions in the solar system. This begs the obvious question: why hasn't Pluto and Neptune collided? The gravitational pull of other planets holds the key to the solution. Not long after Pluto was discovered, astronomers started studying its orbit. At first, they had trouble comprehending its peculiar path. Pluto's orbit stood out due to its steep inclination and elliptical shape, in contrast to the orbits of the other planets, which are relatively near to the ecliptic plane. When it was discovered that Pluto's orbit truly overlaps Neptune's, the puzzle became much more complex. Pluto's orbit stability in the face of these complications is evidence of the complexity of space mechanics. The three-body problem in space science deals with the motion and gravitational interactions of three objects in space, such as Pluto, Neptune, and the Sun. It's similar to attempting to forecast their future paths based on their initial positions and mutual forces. This problem for Pluto illustrates the intricate interaction between its journey, Neptune's path, and the gravity of the Sun. This problem includes the phrases latitude libration and alpha libration in addition to the VZK oscillation. According to astrophysicists, a phenomenon known as alpha libration is responsible for maintaining all planets in their orbits. This phrase, as it relates to Pluto and Neptune, indicates that Pluto is at least 90 degrees distant from Neptune at all times it crosses its orbit. Their paths cannot collide because of this spatial separation. In contrast, the vertical movement of a celestial body inside its orbit is referred to as latitude libration. This implies that Pluto is located much above the orbital plane of every major planet, including Neptune, when it approaches them, offering an extra degree of protection from possible collisions. The VZK oscillation, which bears the names of three scientists who investigated space travel, Bond, Zipperl, and Kai, is another important element in this formula. It concerns the gravitational force that three celestial bodies, Pluto, Neptune, and the Sun, have on one another. Their motion is influenced by this pulling, and in the case of Pluto, VZK explains why its orbit around the Sun is so peculiar. Pluto's orbit appears disorganized, but this oscillation keeps it traveling smoothly for a considerable amount of time. The VZK oscillation demonstrates how, despite the appearance of chaos and randomness, there are patterns and laws that maintain order in space. Pluto's orbit is stabilized by all of these parts, which prevents it from colliding with Neptune or deviating from its path. Understanding how these routes vary according to the forces these space objects exert on one another is made easier with the help of this three-body problem. We can learn more about Pluto, the solar system, far-off worlds, and their stars by studying this. In spite of these steady characteristics, Pluto's orbit is technically chaotic, with small variations in starting conditions resulting in large variations over millions of years, according to numerical models conducted in the late 1980s. Nonetheless, it has been shown that these distinct characteristics of Pluto's orbit preserve stability over extraordinarily long durations, thereby containing the chaos. New simulations have improved our understanding of how major planets such as Neptune, Jupiter, and Saturn impact Pluto's orbit around the Sun. Neptune and Pluto share a unique relationship. Neptune completes 3 orbits around the Sun for every 2 that Pluto completes. In addition to Neptune, Jupiter's gravity and Saturn's assistance also contribute significantly to the safety and stability of Pluto's orbit, which is maintained by this relationship. These experiments demonstrate that Pluto can remain on a stable course for billions of years due to Jupiter's gravitational pull alone. It appears as though Neptune, Jupiter, and Saturn are collaborating to ensure Pluto continues to travel through space securely and without incident. The order and predictability of space bodies' movements depend on these phenomena in the grand scheme of things. The solar system as we know it would be far more chaotic and unpredictable without these systems. Pluto and other bodies have the potential to collide or be ejected from stable courses, which might have a cascading effect on other celestial bodies. For Pluto, knowing its orbit is crucial, particularly in light of the speculation that it may collide with Neptune in the future. This helps us understand the dynamic character of the solar system better. The Pluto scenario shows how complicated interactions between orbital mechanics and gravitational forces may bring even the most seemingly unstable orbits to a state of equilibrium. It also demonstrates how crucial it is to keep tracking and studying these phenomena in order to gain a deeper understanding of our place in the cosmos. We are frequently forced to face the unpredictability of celestial bodies when exploring the depths of space, and Pluto's orbit is a perfect illustration of this unpredictability. Pluto is a prime example of the idea of orbital chaos, which is the delicate reliance of a celestial body's trajectory on its beginning conditions. This implies that a dwarf planet's long-term journey in the vastness of our solar system can be drastically altered by even little changes in its position or velocity. Pluto has a special place that makes it difficult to grasp how planets are classified and how they move. Pluto has been the subject of in-depth research since its discovery in 1930, which has produced important discoveries regarding its makeup and behavior. Pluto's surface, a complicated tapestry of ice, rock, and other compounds, is one of its most interesting aspects. When the New Horizons spacecraft passed by Pluto in July 2015, it delivered previously unheard-of information on this far-off planet. Deep valleys, lofty mountains, and expansive plains define Pluto's landscape. A prominent characteristic is the Sputnik planum, an enormous heart-shaped plain made mostly of nitrogen ice. This region exhibits a wide range of geological phenomena, such as massive icebergs and glaciers that seem to be flowing. These traits suggest that Pluto, despite its extreme cold and distance from the Sun, might still be experiencing geological activity. Pluto's atmosphere is another fascinating feature. It is primarily nitrogen-based, with small amounts of carbon monoxide and methane. Despite being tiny, Pluto's atmosphere shows interesting seasonal fluctuations. Pluto's atmosphere can grow and shrink as it gets closer to the Sun in its extended orbit. Pluto's complex interaction with its surroundings is reflected in its dynamic behavior. Some of the atmospheric gases may freeze out onto the surface when it gets closest to the Sun, then sublimate back into the atmosphere when it gets further away. The system is further complicated by Pluto's interaction with its largest moon, Charon. With a diameter that is almost half that of Pluto, Charon is comparatively huge in relation to Pluto. Rather than Pluto merely spinning around Charon, this size ratio indicates that both bodies are in a mutual orbit around a point in space that lies between them. This special link affects the orbits of other objects in the Kuiper belt and adds to the complex gravitational dynamics in the area. Numerous other dwarf planets and possible impactors can be found in the Kuiper belt, an area beyond Neptune inhabited with tiny icy structures. This belt stores old material from the early solar system, giving scientists insight into how the solar system formed. Pluto's orbital features may provide information on these far-off objects' migratory patterns, indicating that interactions with larger planets may have been a significant factor in forming their present orbits. Comprehending Pluto's orbital dynamics holds significant implications for our understanding of the solar system's evolution. Smaller things, especially those in the Kuiper Belt, can have their trajectories changed by the gravitational pull of neighboring big planets like Jupiter and Neptune. These interactions may cause orbital changes, which may cause collisions or expulsions from the solar system. Researchers may find more general patterns governing the behavior of celestial bodies throughout the galaxy as they continue to examine the subtleties of these interactions. Philosophical issues about astronomical classification are also brought up by Pluto research. Pluto's 2006 reclassification as a dwarf planet sparked contentious discussions about what exactly qualifies as a planet. Many have wondered about the ramifications of such classifications, as the International Astronomical Union's definition placed a strong emphasis on factors like size and orbital dominance. The continuous discussion underscores the necessity of a flexible system for classifying celestial bodies and reflects our growing understanding of the universe. Furthermore, Pluto and the Kuiper Belt exploration potential remains an interesting frontier. Scientists hope to send more spacecraft to explore not only Pluto but other far-off objects that have similar orbits, thanks to technological and mission planning advancements. These kinds of missions might yield important information on the early materials that formed our solar system, which might reveal information about the beginnings of life on Earth. The function of exoplanets, or planets outside of our solar system, is an additional exciting field of research that touches on Pluto's story. With an increasing number of exoplanets found, especially in the habitable zones of their stars, hypotheses concerning planetary creation and habitability can be influenced by knowledge gained from researching our own solar system. The circumstances that support geological activity, atmosphere retention, and stable orbits may shed light on the possibility of extraterrestrial life. Ultimately, the mysterious nature of Pluto and the breathtaking photos that the New Horizons mission has returned have kept the public interested in the planet alive. People all throughout the world are fascinated by the dwarf planet, which has rekindled interest in the immensity of space and our place within it. We are constantly reminded of the countless treasures the universe has to offer as we work to solve the riddles surrounding Pluto and the celestial bodies that inhabit its region of space. Are there any special qualities about Pluto that go beyond its composition and orbit? In addition, it provides an essential case study for comprehending the dynamics of celestial bodies and planetary formation. Pluto and other Kuiper Belt objects are thought to have formed together in the early solar system. By examining its makeup, hypotheses regarding the genesis of terrestrial planets, including Earth, may be informed by insights into the conditions that prevailed throughout the early solar system. Pluto may have a subterranean ocean, according to recent research. This discovery could change our perception of Pluto's geology and capacity to support life. Certain parts of Pluto's surface, including the icy mountains, may be made of water ice, which behaves differently at low temperatures than other types of rocks, according to data from the New Horizons probe. This finding raises interesting issues regarding the existence of life, even in such harsh circumstances, and begs for more investigation into the likelihood of liquid water residing beneath its frozen crust. Furthermore, insights into atmospheric science can be gained from Pluto's interactions with its surroundings. Its thin atmosphere's seasonal variations provide a planetary-scale natural laboratory for research on atmospheric dynamics. Researchers are especially interested in how intricate weather patterns resembling those seen on larger planets can arise from the interaction between solar radiation and the surface. It is impossible to exaggerate the significance of continuing to monitor Pluto and any comparable astronomical entities. We anticipate a plethora of fresh data that challenges current hypotheses and broadens our understanding of planetary science as future missions, including those aimed at the outer regions of the Kuiper Belt, are planned. Every new finding completes the picture of the history of our solar system and the mechanisms guiding its development. Pluto continues to be a symbol of the ongoing search for information about the universe thanks to these studies, encouraging both scientists and amateurs to consider the mysteries that exist outside of our planet.